From Pythagorean to 4-2 fuzzy sets. Well, Pythagorean fuzzy sets, or perhaps it would be better to call them Pythagorean intuitionistic fuzzy sets, were introduced by Jaeger in 2013. And then some, or maybe even many extensions and generalizations of this idea appeared in mathematical community. For example, in 2020, Jaeger and Senapati defined Fermatean fuzzy sets. Then there were so-called 3-2 fuzzy sets of Ibrahim Al-Shami and Al-Barbari. It was in 2021 when they introduced them. And finally, in the current year, in 2022, Shanmati and Nirmala Irudayam founded 4-2 fuzzy sets, and in each case appropriate topological spaces and basic topological notions, interior, closure, boundary, or continuity have been introduced too. Let us start from the very idea of fuzzy set and intuitionistic fuzzy set of Atanasov. If we have a non-empty universe X, then we know that a fuzzy set is a collection of pairs such that for any element of our universe, we define its level of membership in this fuzzy set. So we may identify fuzzy set with its membership function, which takes values between 0 and 1 and corresponds to the concept of characteristic function of a crisp set. In case of intuitionistic fuzzy set, we have two functions, membership and non-membership, alpha and beta, for example, and they are independent. Each of them takes values from 0 to 1, and there is an assumption that their sum for each element R should not exceed 1. Alpha plus beta lesser than or equal to 1. And what's the problem now? Because we have Pythagorean and Fermatian fuzzy sets, and they expand this set of possible values of membership and non-membership functions. Why is that so? Check the idea of Pythagorean fuzzy set. Instead of the sum of alpha and beta, we have the sum of their squares, like in Pythagorean theorem. Alpha square plus beta square is not bigger than 1. Note that, for example, if we have 0.75 or 3/4 and 1/2, then their sum clearly exceeds 1, is greater than 1. But we may sum up the squares of those numbers to obtain 13/16, and this is lesser than 1. So in case of Pythagorean fuzzy sets, we may use 3/4 as the level of membership and 1/2 as the level of non-membership. And all those authors present some potential applications of this concept. Analogously, in case of Fermatian fuzzy set, we have the third power. Yes, we sum up cubes of those membership functions. For example, 0.85 cube plus 0.65 cube. This result is not bigger than 1. It's lesser. In fact, it's lesser than 1. And we may also define so-called degree of indeterminacy by f. And in case of Fermatian fuzzy sets, it's the third root of 1 minus the sum of cubes of membership and non-membership, as you can see here. The interpretation is clear, yes. Alpha cube plus beta cube plus pi cube will give us 1, of course. And these concepts are modified. They've been modified by other authors which I've mentioned in introduction. So, for example, we have 3-2 fuzzy set. In this case, we have alpha cube plus beta square. Yes, and this should be lesser than or equal to 1. And this is the concept of Ibrahim Al-Shami and Al-Barbari, as we already know. And they wrote in their paper that the set of 3-2 fuzzy membership grades is larger than the set of intuitionistic membership grades and Pythagorean membership grades. And moreover, they define their degree of indeterminacy as the fifth root of, as you can see, 1 minus alpha cube plus beta square in brackets. This is because alpha cube plus beta square plus pi to the power of 5 gives us 1, and on the other hand, this degree is 0 whenever alpha cube plus beta square are 1. And on this picture, we reproduce it from the paper by Ibrahim Al-Shami and Al-Barbari. We can see what are the differences between all the classes introduced above. Yes, this is taken from their paper. As we can see, in case of Pythagorean, in case of standard intuitionistic fuzzy sets, we have this triangle of possible grades. In case of Pythagorean sets, we have sector, we could say upper right sector, 1/4 of a circle, and then we have a cube plus beta square. This is the case of 3-2 fuzzy sets. And then we may think about 4-2 fuzzy sets. Again, the idea is simple and is similar to those ideas which I've already mentioned. We have that alpha to the power of 4 plus beta to the power of 2 is lesser than or equal to 1. We have the degree of indeterminacy. In this case, it's 6th root. Everything is similar, nearly the same. So from the purely mathematical point of view, these concepts, maybe they are not very original, but we can imagine some applications. Yes, if someone needs such degrees of membership and non-membership, then one can use those 3-2 or 4-2 or Fermatean fuzzy sets. Of course, in each case, we have basic algebraic operations, but they are defined in a standard manner, just like for intuitionistic fuzzy sets, that the intersection of two sets is for any small x which belongs to our universe. Intersection is defined as a minimum of memberships and maximum of non-memberships. As for the union, it is maximum of memberships and minimum of non-memberships. And as for the complement, as you can see, we just reverse the order of membership and non-membership. Perhaps in the next video we will discuss topological approach to those sets. Here is the bibliography. Here is the newest paper about 4-2 fuzzy sets. And here are all those papers about Fermatean fuzzy topological spaces, 3-2 fuzzy sets, Pythagorean sets, and Pythagorean topological spaces. Thank you very much for your attention.